I mentioned it's the Gaussian noise and it's the PDF of the Gaussian noise, and you can see it's similar to the Gaussian function that here we use as a noise. And also you know that around 68% of the values are in this area between mu, we call it mean here, mu minus sigma and mu plus sigma, and 95% of the value are in this range, that is mu minus 2 sigma and mu plus 2 sigma, that's it's here and here. Later we will use this shape and PDF, then I will draw it here. Okay, for the Gaussian, I'll shape like this. It's a little close to that. Okay, for Gaussian, okay, we have this PDF for Gaussian. Next noise function that we want to talk about, this is Rayleigh noise. This is the function that you can find this noise in your image, and also you can easily find the mean, that we call it mu, and variance of the function or variance of the noise by this equation. And also we have a PDF of the Rayleigh noise here that is like this. Okay. Okay. The next noise is the gamma noise. Also, you can see the PDF of this function, and also the function you can find it here. Also, we can find the mean and variance of the function by using this equation. You have to memorize this shape or PDF of the noise, because later we have to estimate the noise that is in the image. Something like this. Okay. Yeah, another noise that we call it exponential noise. The PDF is like this, and the function is like this, and also you can find the mu or mean or variance of the function like with these equations, and yeah, PDF shape like this, or exponential noise. Okay. The next one is the uniform. So we have this PDF for this function, and also the function is here, and we can easily find the mean of the noise and variance of the noise by using this equation. And also we know that the PDF of noise is like this, uniform. Also the last one is impulse noise, that we call it salt and pepper, because in this noise we have a positive value or negative value. We call the negative value as a the negative value as a black color that is similar to the pepper, and positive value as a white is equal to salt. And we have a PDF like this. Okay. So we know some PDF of the noise that is in the image. Now we can easily estimate the noises. Then after that we can use some operation to remove the noises from the image. For example, if you consider this image as an original image, we have 3-level grayscale, black, gray, and close to white. We have the histogram of the image is like this. Black part that is here, we have here, and gray, and the values that are close to the white, or 255. And also, if we assume that for the degradation function we use just some noises, it means that we just add some noises to the image, but we don't use any degradation function to decimate the image. We just have some noises in the image. Now, we can easily see that, for example, we have some noisy image, and here we have some histogram of the image. And you can see easily histogram of the noisy image. We can see that we have a PDF like this that's similar to this, but it's not exactly the one. And for wavelength, we know that it's similar to this. For the gamma, you can see it start from here, go to the peak values, and it's like here. And also for exponential noise, the image that is noisy by using the exponential noise, uniform, and salt and pepper. Also, we can easily see that the PDF of the image is similar to the PDF of the noise functions that we talked about this before. And also for uniform, we have a shape like this. It means that PDF of this is like this. And for salt and pepper noise, we have PDF of the PDF of the image is like this, and also you can see that we have a PDF of function for this. It means that you easily can estimate the noise in the image by find the histogram of the image and estimate the noise on there according to its PDF. We have two type noise reduction. That one of these is by using the apply some operation on the sensor device, and another one is some functional operation or filter that we can use for the image that is taken by that sensors. We can easily estimate the noise in the image. We have to crop part of the image. For example, we cut a part of the image, for example here, from this, but it doesn't matter, you can easily cut it from this area or this area. But in this example, we cut a piece of the image here, and then we want to find the histogram of this piece of the image. And also you can see when we find the histogram of this part, for example, when we have the Gaussian noise in the image, you can find this PDF. It's same, it's similar to this. And for the wavelength, we have a PDF like this, and for uniform also we have something like this. That's the PDF, and we can easily detect the noise in your image. When we know that most of you passed the probability course, and when we know that the PDF of a function, we can easily find the mu or mean or variance of the function, then it's easy that we use this equation to find the PDF of the. Then when we have the PDF, when we have the mu and variance of the function, easily you can find, for example, A, when we have the A and B here, for example, A here, B here, or A here, B here, and also for that operation we can easily find the the region of the noise in our image. Also, if we consider that for the degradation of the image, we just use the additive noise. It means that we just add some noises to the image. We don't use any decimation function or degradation function. We can easily decimate the image by add some noises. This is the original image plus some additive noise, delta x, y, and we have decimated image, or in this case we call it noisy image. We don't call it decimated image, we call it noisy image. And also, if we transform the noise and the image to the frequency domain, we can easily similarly add the noise to the transform of the image in the frequency domain, and then we find a noisy image in the frequency domain. And if we transfer it to the time domain, we can easily see that we have an image similar to this, but some error will be appear during the transform the image to the frequency domain and inverse transform to the time domain. Also, you know that when we add some noises to the image, we can't, and after that we estimate the type of the noise, we can't just use some subtraction to remove or reduce the amount of noises in the image. It means we have to use some filters to reduce the amount of the noise in the image, because then the noise is distributed in the all parts of the image. Then we have to use some filters to remove this. And it's suggested that don't use these filters, or when you want to work on the noise reduction or something like this, you don't need to go to the frequency domain. But if you have a periodic noise in your image and you know it, or you estimate it, you detect it in the image, it's better that you go to the frequency domain and apply the filter on them. But when you don't have any periodic noise, it will be better that you do it in the spatial domain. But also you can get it in the frequency domain, but it has some cost for you or your algorithm. We can use two types of the filters, or two categories of the filters. The first category is mean filter, that we have 4 types of this filter according to the different means that we talked yesterday about them. The first one is arithmetic mean filter. We can restore the image by using this equation. It's, you can see this mean. It's when you want to find the mean of the image, you can easily use this. And also when you use this function to reduce the amount of noise in your image, of course that after applying this filter you will get a smooth image, and the noise will remove from your image by blurring operation. It means that after applying this filter, although we reduce the amount of the noise in the image, but we have a smooth and blurry image. Not too much, but we have a little blurring in the image. Another filter that we can use in the category of the mean filter is geometric mean filter. You can restore the image by using this equation. It's a restored image. It's not exactly the original image. We can use the multiplication of GST. This is the filter that we use for the noise reduction. And also, after applying this filter on the image, also we have a smooth image, but we keep more details in the image. It means that compared with the arithmetic mean filter, we have in this case we have more details of the image. And the next one is a harmonic mean filter that we used for noise reduction in the image. You can use this equation to restore the image, and also this filter works well for some noises such as Gaussian noises and some noises such as salt and pepper impulse noise. The last type of the mean filter is the counterharmonic mean filter. We can use this equation to restore the image, and it has more effect on the image that has the salt and pepper noise. It means that when the Q, that is order of this filter, is a negative, we eliminate the salt noise or the white point in the image, and we consider the Q as a positive values. We will remove the pepper noise in the image, and you know that if we put the Q equal to 0, we have an arithmetic filter, and if we consider the Q as a -1, we have a harmonic filter. But here we can see an example of this. Consider this as an original image. We added the Gaussian noise to the image with the mean of the 0 and variance of the 400. Then we will apply a 3x3 arithmetic mean filter on the image and 3x3 geometric mean filter. And you can see rather than this image, compared with this image, we have sharper details in the image. If we zoom on some part of the image, we can easily that we have smooth border or edge here, rather than this one that we have a sharp edge after removing the noise from the image. I know that some of you has the project of the super resolution denoising and something like this. I think you can in your project, it's the filters that you can use to remove the noise from your image. It will be useful for you to have these filters. And also, if we add pepper noise, it will be just add the dark point to the image. And for example, we consider this as a salty noise image. It means that we add some white points to the image, the value of the 255 in the 8-bit image. after applying the counterharmonic filter on the pepper noisy image, we can see that the filter removed all pepper noise or dark points in the image. And also, if we apply the counterharmonic filter that has the order of -1.5, we can see that we removed all impulse noise, that's the unipolar, because when we have the actually when we call a noise salt and pepper, it means that's bipolar. It means that we have salt and pepper noise in the image. But for example, in this case, that we just have the pepper noise, and or this that we just have the salt noise, we call it uniform salt and pepper noise. But the other category, another category of the filters that we can use for the noise reduction in the image is order statistics filters, that similar to the previous the mean filter category. It consists of three types of the filter. The first is medium filter, that we can easily restore the image by using this equation or this function, and it has more effect on the bipolar and unipolar impulse or salt and pepper noise. You see that we remove salt and pepper noise by using the counterharmonic filter, but when we use the median filter, we will keep more details in our image and we just remove the noises. Another filter that we can use for the noise reduction is max and min filter. These are two filters. Max filter, that we can restore the image by using this function. It's useful when we want to reduce the amount of pepper noise in the image. It means that it's useful for finding the brightest points in the image. But when we use the min filter, we can remove the salt noises from the image and keep the darkest points in our image. The last filter in this category is midpoint filter. That's the summation of combination of the max filter or min filter when we find the average of this. And we can use this filter to remove the Gaussian noise or uniform noise, and also we can use it for salt and pepper, but in most of the cases it fails to remove the noises from the image, salt and pepper noise from the image. Here you can see an example of the image that is that added some salt and pepper noise to them. Then it's used after applying the medium filter. Then when we apply the medium filter again on this image, you can see this, it's the second pass, and for the third pass we have this image. As you can see, I hope that you can see, there is some pepper noise in, for example, this part, and also here we have the pepper removed. The pepper noise remain in the image by after applying the one-time medium filter. But As you can see, the pepper noise is some of these noise removed here and here, and for the third pass you can see that we totally removed the pepper filters. As you can see here again some pepper's noise remain here, and after the third pass we remove totally all the pepper noises. And also here you can see an image that we add some pepper noise. It means that we add some dark points to the image. If we use max filter, that we mentioned that it will be good for the pepper filter, that we find it will find the brightest point in the image, and then we can, after applying the max filter on the image, we easily remove the pepper noises in the image, but as it's used to find, this filter is used to find the brightest points of the image, you can see here some dark borders are removed. For example, rather than here, you can see we remove some dark border here, also here. That it depends on the application, but it will not good for us to remove some borders, because if we want to use this image for the edge detection, when we remove the border, it means that we will lose some edges in our image. And also you can see here an image that we had some soft noise to the image. Then we will use some mean filter to remove that salt. You can see it's really good for remove the salt noise from the image, but some disadvantage of this filter is that some, for example, white dots. For example, if you can see here, there are some white dots here, but when after applying the mean filter on that, we have darker points compared with the original one. And the reason that why I say that we can't restore this exact image after applying the noise or adding the noise to the image, but although that we know the type of the noise, but we can remove totally noise from this, or if we remove totally the amount of the noises in the image, also we will remove some details or information in our image. We finish our talk by this lecture. We finish our talk about the frequency domain, spatial domain, and also we finished talk about some filtering that we use for sharpening, smoothing, and noise reduction. After this lecture, we will talk about the image compression, and after that, we will talk about the color reduction. But before that, I finish this part, I would like to solve an example that was one of the questions in the last year final exam. I will solve it for you, and we finish this topic. We will finish this topic today. Okay? Okay. We have this 8-bit image here, and we have the pixel values, corresponding pixel values here. Then we have to find something here. See that given 8-bit image match, and this 50 pixel values in the table. Perform the following tasks. Okay. A. Suggest a 3x3 smoothing filter mask and calculate the response at pixel location 2, 3. Okay. And suggest me a smoothing filter to do some smoothing on the image. Do you remember any smoothing filter mask? We talked about these filters 2 weeks ago when we talked about the filtering in the spatial domains. For smoothing, suggest a filter mask. You can go through the slides 2 weeks ago, 2 or 3 minutes time to find and suggest a filter mask. I'm sure that it will be in your final exam, and it will be good if you know this. Maybe
Gaussian kernel.
for a smoothing. Exactly in that slide there was 2 smoothing filter that we showed that we can use for the smoothing in the image. What is it? At that lecture that we talked about some logic operation and something like that. At the beginning we talked about that, and after that we talked about some. And also we talked about the convolution and correlation on that lecture. Also, after finding the filter, please try to find the pixel at this location, 2, 2, 3. At 5 minutes, try to find this, and after that I will solve this. In spatial, yes. Because all image in spatial, we don't have it in the frequency domain. Means you have to find the filter, smoothing filter, and after that use a convolution to find the pixel value of.
So averaging filter.
Yes, it's averaging filter. It's the filter that we use for the smoothing. But what's the pixel value in this location after applying the average filter on that? You know that we can use an average filter mask. Okay. We write it 1/9, 1/1, or you can write it like this: 1/9, 1/9. Okay. We have this filter for smoothing, but what is the pixel value after applying this function, this kernel on the image that we have there?
3.
The pixel location 2 by 3. 1, 2, 1, 2, 3. Instead of 25, no, 3 is not 2, 25. You know that for the convolution, we have to rotate the filter with degree of 180, but in this case, as you can see, if we rotate the filter, we have the same this, but when you have the filter mask that if you rotate it, it will be changed, you have to rotate it if they ask convolution on this. And you know that for filtering or when we want to apply some smoothing filter and sharpening filter on the image, you have to use convolution. But when you want to find the matching on the image, the matching the template by the image, it will be better if you use correlation.